The next thing, which is very, very important in quantum mechanics, is the non-commutativity of operators. So this has to do with physical observables. Like you've all heard of Heisenberg uncertainty principle, like how you cannot measure both the position and the momentum of a particle in the same direction. And so this stems from a mathematical structure called non-commutativity. So if I take the spin matrices Sx, Sy, and Sz that you saw before and calculate their commutators, I think I told you this is going to be IH bar of Sz, etc. Right? Now, the comment that I want to make is that like two operators or okay, let me put it in a positive way. Only commuting operators can be measured simultaneously, okay? So for example, if I take the S squared operator and I evaluate its commutator with, say, Sx, they commute. That means that the total spin and the x component of the spin can be measured simultaneously. Same with S squared and Sz. So you can measure the total spin squared and the Z component. But because Sx and Sy do not commute, these you cannot measure simultaneously. And things that you cannot measure simultaneously are called incompatible measurements or operators, okay, or observables. Okay, so this was from spin. A more famous example is from X and P. If I look at its commutator, you know that X is just X and P is minus IH bar d by dx. And you know, I can apply it to some generic wave function and work it out. If I work it out, it becomes IH bar psi of x. In other words, I can say as an operator equation, the commutator of x and p is IH bar times the identity operator. Okay, so this is the reason why the position and the momentum of a particle cannot be measured simultaneously. This is the root of the Heisenberg uncertainty principle. Okay, so this is about non-commutativity.